Hi viewers, I am Dr. SJCTNC-Dr.C.DEVI Mary, Assistant Professor of Mathematics, St.Joseph College of Arts and Science, Cuddalore. Today I am going to teach you about Laplace transform. Definition of Laplace transform. Let f of t be a given function of t defined for all t greater than or equal to 0. Then the Laplace transform of f of t is denoted by L of f of t, or we can denote capital F of s or small f dash of s, and it is defined as L of f of t equal to integral 0 to infinity e power minus st f of t dt. So we can denote this as phi of s also. This provided the integral exists where s is a parameter. This is real or complex. This is the definition of Laplace transform. Next we see Laplace transform of some elementary functions. First one, L of 1, which is equal to 1 by s. L of 1 equal to 1 by s. Now we can prove this by using the definition. By definition, we can write L of 1 equal to integral 0 to infinity e power minus st f of t dt. So here f of t equal to 1. So you substitute 1, which is equal to integral 0 to infinity e power minus st into dt. Now we can integrate this. We get e power minus st divided by minus s. Now substitute the limit 0 to infinity. When you substitute this one, upper limit minus lower limit, will get 1 by s. So L of 1 equal to 1 by s. Here this s must be greater than 0. The second result is L of e power at, which is equal to 1 by s minus a. Similarly, we can prove this by using the definition. So L of e power at equal to integral 0 to infinity e power minus st e power at into dt. Here f of t is nothing but e power at. E power minus st into e power at, which can be written as e power minus of s minus a into t into dt. Now integrate this one, we will get e power minus of s minus a into t divided by s minus a. Here the limit is 0 to infinity. Now substitute the limit. Here 1 by s minus a, you take this term as common. Now you substitute the limit for e power minus of s minus a into t. When you substitute this one, we will get upper limit e power minus infinity, that is 0. So minus of, when you substitute the lower limit, you will get 1. So minus into minus plus. So we will get 1 by s minus a. Here also s must be greater than a. This is second result. So similarly we can prove for e power minus at. That is e power minus at equal to 1 by s plus a. The second result is L of sin h at, that is the fourth one, which is equal to a by s square minus a square. Proof. We have sin h at. Sin h at can be written as e power at minus e power minus at divided by 2. By definition of Laplace transform, we can write L of sin h at, which is equal to L of e power at minus e power minus at divided by 2. By applying algebraic property of Laplace transform, we can write 1 by 2 into L of e power at minus L of e power minus at. Now this 1 by 2 is a constant. We can take a Laplace transform for L of e power at, then L of e power minus at. We know that L of e power at equal to 1 by s minus a. and L of e power minus at equal to 1 by s plus a. So now take LCM. When you simplify this one, we will get a by s square minus a square. Here this s is greater than modulus of a. So the result is L of sin h at equal to a by s square minus a square. So similarly we can prove for L of cos h at. So that is s by s square minus a square. The next result is L of sin at, that is a by s square plus a square, and L of cos at, which is equal to s by s square plus a square. Both the term s must be greater than 0. Now we are going to prove both by using Euler's formula. So we know that e power ix can be written as cos x plus I sin x. So instead of x, replace at. So e power I at, which is equal to cos at plus I sin at. Now take Laplace transform on both the side. We will get L of cos at plus I sin at, which is equal to L of e power I at. We know the formula for L of e power I at, which is equal to 1 by s minus a. Instead of a, here we have ia. So replace ia. That is 1 by s minus ia. Now take conjugate for this one. That is s plus ia, and multiply both numerator and denominator by this conjugate. So we have s plus ia divided by a square plus a square. Now take it the real part and the imaginary part, separate and write. So we have s by s square plus a square plus I into a by a square plus a square. Now equating real and imaginary parts, we get L of sin at equal to a by s square plus a square, and L of cos at equal to s by s square plus a square. The next result is L of t power n, which is equal to gamma of n plus 1 divided by s power n plus 1, or we can write n factorial by s power n plus 1. Now we are going to prove this one. L of t power n, which can be written as integral 0 to infinity e power minus st, then t power n dt. So here we cannot integrate directly, so we can use substitution. So put st equal to u. So from this we can find out t equal to u by s, dt equal to du by s. Now substitute and simplify this one. We will have integral 0 to infinity e power minus u into u by s the whole power n into du by ds. Now take power separately both for numerator and denominator. When you simplify this one, you will have 1 by s power n plus 1 into integral 0 to infinity e power minus u into u power n du. Now in the power you add plus, add and subtract 1 here. We will have u power n plus 1 minus 1 into du. Now this is in the form of integral 0 to infinity e power minus x into x power n minus 1 into dx. So this is the formula of gamma of n. So instead of n, here we have n plus 1. So by using the definition of gamma of n, we can write gamma of n plus 1 divided by s power n plus 1. Here this n is greater than minus 1. So instead of gamma of n plus 1, we can write n factorial. So the result is L of t power n equal to n factorial by s power n plus 1. Thank you.